Hello all. Today we will see descriptor tables. Up till now we had studied how a descriptor's format is, what different types of descriptors are, what is a selector, what is the format of a selector, how actually the address is getting translated with the help of a diagram. We have seen all these things. Now, today we will see actually what descriptor tables are. There are total 3 descriptor tables: GDT, IDT and LDT. GDT means global descriptor table, IDT means interrupt descriptor table, and LDT means local descriptor tables. So let's start with these tables. As mentioned earlier, the segment descriptors are grouped and they are placed one after the other in a continuous memory locations. This group arrangement is known as the descriptor table. Now, how is the descriptor tables format? It is nothing but a continuous memory location. And in these continuous memory locations, the segment descriptors, no, they are grouped or they are placed one after the other or one top on the other top. Okay. So this continuous memory location or this group is totally called as a descriptor table. So to generalize, the descriptor table consists of a group of descriptor segments. Okay. Then the second point, the maximum limit for the segment of descriptor table is 64 KB. Okay. So if anyone asks you, what is the maximum limit for the length of a descriptor table? Means a descriptor table can have what capacity? So it is nothing but 64 KB. Okay. And we know that each descriptor takes 8 bytes to store the information of a particular segment. Now, by default, if you can remember the diagram that we multiplied the index by 8, selector index by 8. So why did we multiply the selector index by 8? Because the descriptor takes 8 bytes. Okay, by default the descriptor will take 8 bytes to store any type of information. So we used to multiply the what do you say, selector index by 8. So this is the reason why 8 bytes of information is required for storage. So the descriptor table can have how many type of descriptors? One descriptor table can have 8192 descriptors. The upper 13 bits of a selector are used as an index into the descriptor table. Whatever is the upper 13 bits, no, it is used as the selector. The upper 13 bits of a selector, they are used as the index into the descriptor table. Now we'll see how it is. So there are 3 types of descriptors. I hope this is clear. To summarize these 3 points in short, a descriptor table consists of a group of segment descriptors, okay, and segment descriptors together they form a descriptor table. The descriptor, it will take 8 bytes. It is always referred to as 8 bytes. Why? Because it stores the 8 bytes of information. And what is the maximum limit for a descriptor table? It is 64 KB. And so how many descriptors can be stored? 8192 descriptors. And the upper 13 bits of a selector are used as a index. Okay, so we multiply the index by 8 in order to generate these 8 bytes of descriptor. So how many types of descriptors are there? GDT, IDT and LDT. This GDT, it is nothing but it is a general purpose table of a descriptor. So it is called as it is a general purpose table, so it is called as a global descriptor table. And this table can be used by all the programs to refer the segments of the memory. So let that program be of any type, all the programs can refer or all the programs can use this GDT table. Okay. So the GDT can have any type of segment descriptor except for the descriptor which are used for serving the interrupts. So very important point. Global descriptor tables, they can have all the type of segment descriptors except one type. Which is that type? That is interrupt. So for interrupt, service of the interrupt is provided by some other category, not by global. Hence, global is having all the category, all the rights except the interrupts. Now, interrupt descriptor table. Now, this table will hold the segment descriptors that define the interrupt or exception handling routines. Now over here, see what was global doing. Global will have a reference, or it can hold all type of descriptors, but except which type of a descriptor? Interrupt descriptor. It interrupt services it will not handle. Then who will handle this interrupt services? This IDT, interrupt descriptor table. So interrupt descriptor table is such a type of table that will hold the segment descriptors that define the interrupt or exception handling. Okay, so these are special case tables we can see. So the IDT is a direct replacement for the interrupt vector table used in a 8086. The 8086 microprocessor, no, it was having a it was having a table, interrupt vector table. This interrupt vector table was used for handling the interrupt services. So now in 80386 this interrupt vector table is directly replaced by IDT, interrupt descriptor tables. So this is very important point. Local descriptor tables. Now what does this LDT do? It is nothing but such a type of table that only a unique program can refer that table. Not all the programs can refer that table. So it is given over here. They are set up in the system for the individual task or closely related group of tasks. Individual task or closely related group of tasks, they can use these tables. Then the second point, the following figure shows how tasks use its individual memory area defined by the descriptors from the corresponding local descriptor table, and how it shares the memory area defined by the GDT. So what there is a diagram given over here, and there are individual tasks, or these tasks are named as task 1, task 2, and task 3. Also it is having task 1 local address space, task 2 local address space, and task 3 local address space. The middle one is nothing but the global address space. This is nothing but the global. Any program can refer this space. But this is LDT local descriptor. This is LDT local descriptor. Again, this is LDT local descriptor. So what does this tell you? This diagram tell you that the descriptors that are stored in the descriptor tables are nothing but related to their particular memory area. Okay, fine. So it is very important to know that where these tables are stored. In this point, it is given over here. See, it is important to know that where these tables are stored. Now we know that there are tables. These tables are stored in the particular memory area. But in which memory area they are stored, these tables, it is very important to know whether they are locally stored, whether they are globally stored, or whether it is an interrupt table. So it is very important to know the exact location or where these tables are stored. So it is possible to place the descriptor tables anywhere in the processor's address space, and it is not necessary to keep them together. So there is a processor's address space. In this address space, we can place the descriptor tables anywhere, and it is not necessary to keep them together. So in short, what does this it tell you? The processor's address space is available, and we can place our descriptor tables in that processor's address space regardless of keeping them together. Not necessary to keep them together. Now in this diagram, there is one more point, virtual address space. So whatever is the address space between the global and the local is termed as the virtual address space. Oh, again over here, this space between the global and the local, it is termed as virtual address space, and again over here it is termed as virtual address space. So this is task 1's virtual address space, task 2's virtual address space, and task 3's virtual address space. So this is a diagram just telling you how global is placed and how local addresses are placed. Then now we have come to know what are segment, what are selectors. Now we studied what are tables. Now we will come to the point that are registers. Now what is the register doing? Register is nothing but used for storing the contents. Okay, or it is nothing but it is used for holding the address space and whatever data it is. So we will see now how these registers are actually working. Fine. So each table, there is a table. So each table, no, it has a register associated with it. Okay, so let that register be associated with GDT, then it is termed as GDTR, Global Descriptor Table Register. If a register is associated with LDT, then it is termed as LDTR. And if a register is associated with IDT, Interrupt Descriptor Table, then the register itself is termed as IDTR, Interrupt Descriptor Table Register. So just add the letter R when you are using the register word. So it is termed as GDTR. Just add the letter R, then it is termed as LDTR. And here, if you add R, then it is termed as IDTR. Okay. Now, these registers, they contain 32-bit linear address of the base of its descriptor table and the table's limit. The register, what does this register contain? It will contain a 32-bit linear address of the base of its descriptor. Wherever is the descriptor's base address is contained by this register, and also the register will contain the limit of the table. What is the limit of that table? So the base address of a descriptor table is the linear address of the first byte of the first descriptor in the table. This line is bit confusing, so I will simplify it and tell you. Now the descriptor table, okay, the descriptor table is having a base address. Okay, so now from where do you recognize that this is the base address of the table? So it is recognized as whatever is the linear address, okay, linear address of the first byte of the first descriptor in the table. You have a descriptor, okay, in that descriptor you have a first descriptor table. In that descriptor table you have the first byte, okay. In that table, whatever is the first byte of the first descriptor table, that is considered as the linear address, okay. So let that byte be any type of byte, okay. And the limit specifies how long the table is. Whatever is the limit given, no, that limit will tell you how long that table is, and therefore how many descriptors it is having. If the table is having so and so limit, that means suppose 100 limit, then it will contain 100 descriptors. If the table is having the limit of 1000, then it will contain 1000 descriptors, okay. So make this point very clear. The base address of a descriptors table means there is a descriptor table, and how do you will find the linear address? So the linear address of the whatever is the linear address of the first byte of the first descriptor in the table is nothing but the base address of your descriptor table, okay. And limit will specify how long that table is. See, uh, this is nothing but global descriptor table register GDTR. It is consisting of three fields: limit, base address, and this is again a base address, okay. And this will show you this is nothing but the table physical memory. This whole is termed as a physical memory. This memory is again containing of segment descriptors. These segment descriptors are globally termed as one whole descriptor table, and this one whole descriptor table over here is given as GDT, global descriptor tables, and its limit is 8192. Okay, so see, what is the limit now over here? From number 1 to 8192. So the curly bracket is given over here. So 8192 is nothing but the limit. Fine. So what is the base address? The first byte in the table, first byte and the first entry of the first table is nothing but the base address. If your base was over here, suppose this one was over here, then this was your base address of the descriptor table. So this is the base address of the descriptor table over here. Fine. And this is nothing but the remaining address part. So what does the GDTR tell you? The following figure will show the contents of the GDTR register that are used to define a GDT. See, global descriptor table, no, it will define your GDT only. Okay. And it will also define the physical memory address space. This whole box is nothing but termed as physical memory address space. The GDTR is a 48-bit register. If anyone will ask you, what is the length, or what is the, how many bytes, how many bits is the register? It is a 48-bit register that is located inside the 8086 DX. Okay, 8086 DX. So do remember, over here it is given 0 to 47. So what is the length of the register? It is 48-bit. Similarly, now see the next point. The lower 2 bytes of this register specifies the limit. This is the limit, okay, in bytes for the GDT. The value of the limit is 1 less than the actual size of the table. The value of the bit is 1 less than the actual size of the table. Suppose the actual size of the table is 10. So 1 less than the actual size means what? It 9. Okay. Then for example, see, if there is a limit, okay, 03FFH, this is a hex value, then the table is 1024, that is 1023 plus 1 bytes in the length, 1 less than it is given over here, bytes in length, that is 03FFH is equals to 1023 to the base of 10. This is nothing but the terms related to hex value. I will tell you in the normal form. Suppose if the length is 100, okay, then the table is how much it is? Actual value 99. This value is termed as 100, will be termed as 99 plus 1. Okay, and bytes in the length. So how it will give, how it will be given? This value will be represented as equals to 100 equals to 99 to the base of 10. I'm just giving you example. Don't take the numericals as it is. This is actual numericals that are term for the limit. Okay, since the limit of the field is 16 bits long, the GDT can grow up to 65,536 bytes long. See, what is the length or the limit? It is how many bits? 0 to 15 means how much? 16 bits. It is having the limit field of 16 bits long. So how long the GDT, that is the global descriptor table, this table, it can grow. It can grow up to how many bytes? 65,536 bytes long. It can grow long like this, 65,536 bits long. The upper 4 bits of the GDTR specifies the 32-bit linear address of the base of the GDT. This is nothing but 32-bit linear address of the base of the GDT. Okay. Now we'll come to the interrupt descriptor tables. Diagram is same. How it is related now we will see. See, the structure is also same. The physical memory. Now in the global we had the word 88,192. But what is the limit over here? 256, that is 1 to 256. So what is the limit of I see this is again a 48-bit register. It is having limit, base and base. Okay, then 1 to 256 is the limit. Then in middle it is placed as interrupt descriptor table, and the box is termed as the physical memory. So I think they have given 256 because 256 interrupts are there. So we'll relate now how this diagram is shown. Like the GDTR, IDTR holds the 16-bit limit and the 32-bit linear address. Same, 16-bit limit and 32-bit linear address of the base of the IDT. The following figure will show the contents of the IDT registers used to define an IDT. See, the register will always define a table. Let that register be local, global, or interrupt. And it is defining in terms of 80386DX because we are having a 32-bit register and physical memory address space. Okay. Like the GDTR and the IDTR is also a 48-bit in length. Okay. See, it is nothing but 48-bit in length, 0 to 47, with lower 2 bytes defines the limit and upper 4 bytes defines the base address. See, limit and the base address. Since limit field is 2 bytes, okay, what it is termed, since the limit field is 2 bytes, the IDT, that is the interrupt descriptor table, can also grow up to same 65,536 bytes long. Okay, but The 80386DX, it will support up to 256 interrupts or exceptions. Therefore, the size of the IDT should not be set to support more than 256. Excuse me. Why it is given over here 256? Because the interrupt descriptor table, it supports 256 interrupts or exceptions by default. So the size should be 1 to 256 only. Otherwise, it will not be referred to as, if the size will exceed, no, then it will not be referred to as IDT. There will be generated some of the error over there. Okay. Then next is the local descriptor table. The local descriptor table, unlike GDTR and IDTR, the LDTR is a 16-bit register. Okay, it does not specify any limit or base address for the segment. Very important point. It is a 16-bit register. These both were 48-bit registers, whereas LDTR is a 16-bit register. And this register, it will not specify any limit, or it will also not specify any base address for the segment, but it specifies the address of the LDT descriptor stored in the GDT. Global descriptors table is there. Within that global descriptor tables, your local descriptors are stored. So in order to find out the in order to find out that LDTR should locate their particular LDT tables, so what it will contain, what the local descriptor table registers will contain, they will contain the address of the local descriptor table. They will not contain the limit and the address space. Okay. So the following figure shows the LDTR, GDT and IDT. Okay, then what it will show? It shows how many contents of the LDTR are used indirectly. There are some contents, and these contents of LDTR, they are used indirectly to define a local descriptor table. The LDTR holds a selector that points to the LDT descriptor in the global descriptor table. This register, the local descriptor table register, it will hold a selector. Why it will hold a selector? Because it will point to a particular local descriptor table. Why it will point? Because this LDT is stored in the GDT. So in order to identify the local descriptor table, the selector will point to that particular table itself. Okay. Then whenever a selector is loaded into the register, local register, the corresponding descriptor is located in the global descriptor table. Now this is, see how beautifully they have related. Whenever a selector, okay, there is a selector. When that selector is loaded into your register, then the automatically what will happen? The corresponding descriptor, whatever is the corresponding descriptor, it will also be loaded, or it will also be located in your global descriptor table, so that when it will be located in the descriptor table, then they will automatically relate to each other. Fine. So the contents of this descriptor defines the local descriptor table. Whatever are the contents of that descriptor, it is used for defining the local descriptor table. Once the use of this what you say descriptor table is over, then another LDTR will be loaded, and another corresponding local descriptor table will be located in the GDT. Then this cycle will go on continuing. So the 32-bit base address value defines starting point of the table. Whatever is the 32-bit base address, it will define the starting point of the 80386DX physical memory address space, and the 16-bit limit will define the size of the table. It is the diagram over here. Now we'll relate very properly. See, the diagram for the LDTR is very different from GDTR and IDTR. This is nothing but base, 32-bit base address. It will contain the base address and 16-bit limit. Okay, this is 16-bit limit. This is nothing but GDTR, Global Descriptor Table Register. Over here, we are having a selector. Now, why we are using selector? Because selector is used for pointing to the corresponding table. This selector is loaded into the register. Why it is loaded into the register? Because it will do the work of pointing to the required table in the descriptor. There are suppose 100 local tables. Okay. 100 local descriptor tables. So out of these 100, suppose this is the 70 number. Okay. So when this register will load the selector, automatically this selector will start pointing to the 70 number table. So the selector is given over here. See 0, 1, up to so on. There are different types of tables. Then it will consists of this whole thing. This whole thing is nothing but called as global descriptor table, because it is globally defined and it is base address is of GDTR. See, this is GDTR pointing to the base address, because GDTR will always point to the base address of the global descriptor table itself. Fine. Then this is nothing but this area is nothing but comprised of LDT tables, local descriptor tables. Okay. And the limit, see, this limit is pointing over here. This is nothing but the limit of your table, limit of your GDT. This much is the limit of GDT. And the remaining portion, 0, 1, and 2, they are termed as local descriptor tables. These are nothing but local descriptor tables. This whole box is termed as physical memory. What is the address what is the capacity of physical memory? 0, 0, 0, 0, 0 up to FFFFFFF. Okay. Now how it is working? LDTR will have a selector loaded into it. It will point to its corresponding local descriptor table. The GDTR will point to the base address of the global table, and it will also specify the limit of the global table, and others are considered as local tables. So we can say that LDT, local descriptor tables, they by default reside in the GDT, that is the global descriptor tables. Then the GDT can contain many LDTs. This is what we saw over here. The GDT can contain many LDTs. Fine. So to put a particular LDT in the service, it is necessary to load the LDTR with the corresponding selector. If you want to put the table, local table into the service, what is necessary? To load the local register with the corresponding selector. See, load the local register into the corresponding selector. If you want to bring this into service, if you want to bring the local table into service, then load the register into corresponding selector. For loading the values of global register, interrupt register, and local registers, the 80386DX microprocessor, it will provide LGDT, LLDT, and LIDT instructions. Okay. And it also provides SGDT, SLDT, SIDT instructions. Here S means store. Store global descriptor table, store local descriptor table, store interrupt descriptor table. Fine. These instructions, these 48-bit instructions, they copy the contents of the descriptor table register into the 6 bytes. What these instructions? These are nothing but instructions. L will stand for load and S will stand for store. Store the global, store the local, store the interrupt, load the global table, load the local table, and load the interrupt table. So these are 48 bits instructions, and these instructions are used for copying the contents of the descriptor table register into 6 bytes of memory that is pointed by the destination operand. Whatever is the destination operand, it will copy the contents. These instructions will copy the contents. Okay. Then these tables are manipulated by the operating system. Thus, the instructions used for loading the descriptor tables are privileged instructions. There are 4 privilege levels: 0, 1, 2, and 3. Okay. These privilege levels are nothing but associated with the point of view of security purpose, and these are associated with the operating system. So it is nothing but they are used for loading the descriptor tables are whatever are the instruction or the descriptor tables loading purpose is done. They are called as the privileged instructions. The next thing is segment register and segment descriptor cache. Very important point. This is nothing but related to again cache. Cache means memory storage part and register means what contents it can store or hold into it. So the segment register, it contents are segment register contents are used as selector to specify the to select the specific descriptor. Very simple. The segment register contents, whatever are the contents in the segment register, they are used for what purpose? They are used for selector to select the specific descriptor from the descriptor table. If the segment register will contain global contents, then which selector it will use to select? It will select the global descriptor table. If the register contents are local, then they are used to select a specific descriptor. Which descriptor in terms of local descriptor table. So and IDT will select the IDT contents. Okay. So this part of the segment register is visible to the programmer. Which part is visible to the programmer? The segment register part. The following figure, there is a figure over here. It will show the complete segment register with visible and hidden part of it. So the hidden part is referred to as segment descriptor cache register. Whatever is the visible part, segment registers are visible to the programmer and segment descriptor cache is the hidden part that is not visible to the programmer. So using these registers, the DX microprocessor will store the information from the descriptor, thereby avoiding the need to consult a descriptor table every time it accesses the memory. So what is the use of a cache? Cache is nothing but a part of a memory, or it is a quick access memory. So instead of whenever you are wanting to refer to a table, okay, so or whatever information you want from the table, instead of accessing the registers that are stored to the given desired location, there it what it will do, it will avoid that thing and it will consult a descriptor table that is already available in the cache. From that cache memory, it will refer the cache memory and access those contents. So thereby avoiding the need to consult a descriptor table every time it accesses the memory. So this is the main functionality of the descriptor cache. It is an immediate memory access facility. Instead of again and again going and consulting the descriptor table every time, what it will do, it will store the information. These segment register, they will store the information and try to access that memory area. So the segment register, that is the visible portion contents, are manipulated by the programs, and whereas segment descriptor cache register, that is the hidden portion, these contents are manipulated by the processor. Which part is visible? Segment register. So who will manipulate segment register? Manipulate means what? Make changes. The programmer. Okay. And the hidden portion, that is the segment descriptor cache register. This is a hidden part. So who will handle this hidden part, or who will manipulate the contents of this hidden part? The processor. It will be done at the background part. Okay. So once the descriptors are cached, whatever is the descriptor that you want to cache, subsequent references to them are performed without any overhead for loading of the descriptor. Whatever, once the descriptors are cached, no, the subsequent references of that particular cache, they are performed without any overhead. Overhead means what? Duplications are not done in this thing. Without any overheads, they are loaded into the descriptor itself. So this is the biggest advantage of segment descriptor cache register. What is the biggest advantage? The subsequent references are performed without any overhead. This is the biggest advantage. This is the diagram over here. GS, FS, ES, DS, SS and CS. They are nothing but registers. Okay. This is 16-bit visible selector. Out of the whole part, out of this whole part, 16-bit is the visible part of the selector, and the remaining is the segment descriptor cache register. This is the hidden descriptors that are performed or accessed by the processor itself. So this is it from the segmentation translation part. whatever we had studied, that is the local descriptor, global descriptor table, and the interrupt descriptor table, how the registers are formed and accessed, how the selector is used, how it is multiplied, and how their contents are actually accessed by the different address spaces of the memory. I hope you have understood. If any doubts, you all can contact me. Thank you.